In September 2022, NASA's DART spacecraft successfully hit Dimorphos, a small asteroid moon, marking the first time humanity altered the path of a celestial body. The impact was part of a planetary defense test meant to prove that we could deflect an asteroid heading toward Earth using a kinetic strike. It worked. But new findings show that the outcome was more complicated than we thought. Let's explore what this means for planetary defense. NASA's Double Asteroid Redirection Test, or DART, was designed as a controlled experiment. Its goal? Determine if a spacecraft could alter the orbit of a non-threatening asteroid by direct collision. Dimorphos, the 160-meter-wide moonlet orbiting the larger asteroid Didymus, was selected precisely because it posed no danger to Earth. On September 26, 2022, DART impacted Dimorphos at a speed of 6.6 kilometers per second. Ground-based telescopes confirmed the orbit had shortened by roughly 32 minutes, a clear success in terms of the mission's primary objective. But the story didn't end with that shift in orbit. Just behind DART was Liquiacube, a small Italian spacecraft that captured images of the aftermath. These images revealed a chaotic scene. 104 boulders, ranging from 20 centimeters to 3.6 meters, were blasted away from the impact site. Some of these fragments were moving at speeds exceeding 50 meters per second. Crucially, the boulders weren't scattered evenly. Instead, they clustered in two dominant groups, with one major southern cluster accounting for the majority of the mass. The pattern suggested that the debris wasn't just the result of a symmetrical explosion, but of an impact that interacted unevenly with the asteroid's surface features. Researchers believe that DART's solar panels may have struck two large boulders just milliseconds before the spacecraft's body made contact. This may have fragmented these rocks and contributed to the lopsided ejecta pattern. That asymmetry matters. One of the most critical findings from the study concerns the momentum enhancement factor, denoted by beta. This value compares the total momentum transferred to the asteroid, including from ejecta, to the momentum of the spacecraft alone. For DART, beta was estimated to be around 3.6. That means the ejecta contributed nearly 3 times the momentum of the spacecraft itself, effectively delivering a second, larger push. However, this push wasn't perfectly aligned with DART's trajectory. The boulder clusters, especially the one moving southward at shallow angles, created momentum that was perpendicular to the intended path. According to the team's analysis, this could have tilted Dimorphos' orbital plane by up to 1 degree and possibly changed its rotational behavior. This reveals a significant complication in the asteroid deflection strategy. It's not just about how hard we hit an object, but about where and how the asteroid reacts. In a real emergency, where a precise orbital adjustment is needed to steer an asteroid away from Earth, uncontrolled recoil in unintended directions could lead to failure. Worse, it could make the threat harder to predict, especially if the asteroid starts spinning or tumbling after impact. These insights challenge the simplicity of early planetary defense models, which assumed a clean kinetic energy transfer without complex debris dynamics. They also highlight how surface composition and structure can dramatically influence an asteroid's reaction to impact. Dimorphos, as it turns out, isn't a solid rock. It's likely a rubble pile, a loosely held together mix of boulders and dust. That structure plays a key role in how the impact energy is distributed. NASA's 2005 Deep Impact hit a fine-grained comet, creating a smooth plume. DART struck a boulder-rich asteroid, causing chaotic ejecta. The takeaway: asteroid responses vary. One strategy won't fit all. This new understanding is already being applied to future missions, starting with the European Space Agency's Hera mission, which is scheduled to arrive at the Didymos D Morphos system in 2026. Hera's job is to map the crater left by DART, study Dimorphos's internal structure, and precisely measure any changes in orbit, tilt, and spin. These observations will validate or refine the momentum estimates and help scientists improve their models. Lycia Cube provided an essential post-impact snapshot, but Hera will offer sustained, close-range data. That's important not just for understanding DART's outcome, but for shaping future kinetic impact strategies. Beyond Hera, the implications stretch further. If surface structure and impact geometry can dramatically change deflection results, then we need more adaptable toolkits. Kinetic impactors may remain the go-to method for some situations, but other technologies, like gravity tractors, laser ablation, or ion beam deflection, may be better suited for targets with fragile or unpredictable compositions. There are also operational risks to consider. Ejecting large boulders into space could pose hazards to nearby spacecraft, especially if follow-up missions are planned. Any future deflection attempt must now include an analysis of debris management, not just for mission safety, but to avoid creating new threats in orbit. These aren't failures, they're revelations. Every mission uncovers critical variables. Is the asteroid solid or a rubble pile? How does momentum transfer through porous material? Can ejecta recoil create unintended trajectories? Success isn't just moving a space rock, it's mastering deflection across all asteroid types under any conditions with surgical precision. Because when Earth's safety is on the line, there's no room for guesswork, only for deeply informed action. DART didn't just hit an asteroid, it kickstarted a new chapter in planetary defense. It proved impact works, but also revealed the messy reality. Debris recoil, unpredictable ejecta, and orbital shifts. Now, as ESA's Hera mission gears up, the focus shifts from force to finesse. Precision, reliability, and adaptability are the new standards. The future of Earth's safety depends on it. Stay curious, stay ready. This is just the beginning.